space or the null space of A minus I is basically the span of the vector 1 0 0 actually. Okay, so 1 0 0. It's the span of the vector 1 1 0 0. So what does this mean? This means that the geometric multiplicity is equal to 1 because the dimension of the null space of A minus I is 1 actually. Okay. Similarly, you can make a computation about the matrix A. The other eigenvalue, in other words G2. Okay. And in order to do this, you need to find the vectors V such that when they are operated, when A minus 2I is multiplied with this V, it gives you 0. So if you're going to find this actually, so you're going to get this 0, 1, 4, 0, 1, 0, 0, 0, 1 equal to times x, y, z equal to 0, 0, 0. So when you're going to do the computation, you're going to see that the vector v, which is x, y, z, is going to be a vector x, 0, 0 again at. So therefore, the null space of A minus 2I is a vector that is a subspace that is spanned by a vector 1 0 0. So these are the multiples of the vectors 1 0 0. So there is only one vector in the span which span this entire space. So the G2 geometric multiplicity is also 1. Okay? The geometric multiplicity is also 1. Keep in view that the algebraic multiplicity of the two was 2 actually. How about B? I'm not going directly these calculations, I'm just mentioning actually. Okay, I'm not going to repeat the calculation for the matrix B. When you're going to compute for matrix B, you can verify for eigenvalue 1, the matrix B, for eigenvalue 1, if you compute the geometric multiplicity, it turns out to be 2, and the geometric multiplicity for the eigenvalue 2 is also 2 actually. Okay? Is also 2. So that's how you compute the different kind of multiplicity. It's not difficult. Using the minimal and the characteristic polynomial, it is really easy to find the what do you call, the different kind of multiplicities of the matrices. Now I'm going to move towards what do you call the one of the key topics of our discussion today, which is the diagonalization. What are the criteria for a matrix, okay, to say that the matrix is diagonalizable? By the way, all these results and examples that we are doing for matrices, they are also going to be true for the linear transformation as well. In other words, you can also define what is the characteristic polynomial of a linear transformation, what is the characteristic minimal polynomial of a linear transformation, what are the multiplicities, different multiplicities for linear transformation. Because if you have these for matrices, and I know that in finite dimension all linear transformations are matrices, so when I'm saying that what is the characteristic polynomial of a linear transformation, basically I'm saying that okay, what is the characteristic polynomial of matrix representation of that linear transformation actually, and hence all of the properties. So in other words, the theorems that we are proving about matrices are also true for the linear transformation as well. All notions, all these definitions actually, because every linear transformation is basically a matrix actually.